I'm going to look at a few more example problems of evaluating integrals using u-substitution. When I look at an integral like this and I'm going to evaluate it, again, the problem is it's a product. I've got p times something to the 12th, and we didn't have an anti-differentiation rule that allows me to deal with a product, so I need to get this into a better form. Sometimes what we want to do is we want to find something where I take a derivative of part of the integral and that derivative appears somewhere else. Also, often, all other things being equal, we often let my u substitution, we let u equal a more complicated part of the problem. So here, letting u equal p isn't going to do much. If I let u equal p, I just get du is dp. And so I could get rid of this and this, but I'd still have this complicated thing to deal with. If I let u be the whole thing to the 12th, then du, I'd have to bring the 12 down and I'd get that to the 11th as my du, and that's too complicated. I can try maybe just letting u be the inside of the parentheses. Now, if I do that, of course, then this whole thing is going to become just u to the 12th power. What happens if I take du? Well, I take the derivative of 2p is just p, the derivative of 5 is 0, and then I throw on the dp. Now, that's not here exactly. I do have dp, and of course I can get that here. I divide both sides by 2 or multiply by a half. So I'd get 1/2 du is equal to dp. But the problem is I still have this p over here in front, which hasn't been replaced with anything with u. So what I do is I take this statement here where I've got u set up and I solve that equation for p. So I add 5 to both sides. And then I'm going to divide both sides by 2, or I can multiply by a half. So that says now I can replace p with just 1/2 times u plus 5. So that gives me a way of going here. So p is 1/2 times u plus 5. The middle stuff there, 2p minus 5 to the 12th power, that's just u to the 12th. And this last part, dp, is just 1/2 du. And now these 1/2s can be pulled out, factored out of the integral. So a half times a half is 1/4. And all I have left here then is u plus 5 times u to the 12th du. I can go ahead and distribute. U times u to the 12th is u to the 13th. And now I take the antiderivative. So I increase the power by 1. So I'll get u to the 14th. Then I have to divide by the new exponent. And then plus 5u to the 13th, divide by the new exponent. And this is where I get my plus c. Now I just distribute 1/4 times 14. That gives me 1 over 56, u to the 14th. 4 times 13 is 52, u to the 13th, plus c. And now I substitute. I don't want to leave u in my answer, so u was 2p minus 5. That was my original variable. So 2p minus 5 to the 14th. And I get 2p minus 5 to the 13th, and then plus c. In theory, if you really wanted to, you could do some work here where you looked at the fact that those are both 2p minus 5s, and you could factor out 2p minus 5 to the 13th power. I don't know how much that's really going to do for us, so I'm just going to leave it like that. Okay, so this now is a definite integral. With a definite integral, remember what I've really got here then, well, a couple things. These are really x limits then. So what I've got here, this is the limit as x goes from 4 to 12 of this square root of 1 plus 2x dx. Not much choice for my u. I'm probably going to let the inside of this square root be u. So then when I take du, well, the derivative of 1 is 0. The derivative of 2x is just 2, so I get 2 dx. But I just want to have dx here, so that's going to be 1/2 du equal to dx. But the other thing I'm going to do, instead of x equal 4, I'm going to let u equal 1 plus 2x. So that's 1 plus 2 times 4, which will be 9. And instead of x equal 12, I'm going to let u equal 1 plus 2x. So that would be 1 plus 2 times 12, which would be 25. So when I rewrite this, my u limits now, instead of 4, I get 9. Instead of 12, I get 25. I have the square root of u, and I have 1/2 du. So the 1/2 can be brought in front. I've got the integral from 9 to 25 of u to the 1/2 du. Square root is 1/2. So I need to add 1/2 plus 1, that's 1/2 plus 2/2. So that would be 3/2. So I get u to the 3/2, and then I have to divide by 3/2. And this is being evaluated now from 9 to 25. I don't need plus c. Definite integrals, we don't have to worry about that constant of integration. If I'm dividing by 3/2, that's the same thing as multiplying by the reciprocal, which would be 2/3. And then I get u to the 3/2 evaluated between 25 and 9, so I get 25 to the 3/2 minus 9 to the 3/2. So let's see here, these go away. So I get 1/3. And then the 3/2 power, remember the denominator is the root I'm going to take, and the numerator is the power I'm going to take. So the square root of 25 is 5. 5 to the 3rd power is 125. The square root of 9 is 3. 3 to the 3rd power is 27. So I get 1/3 times 98, or that would just be 98/3. Okay, so that's the result for that problem. And let's see, I think I've got one more to look at here. This is sort of like the first one I did in this part 2. I look for a u-substitution. The best I think I'm going to be able to do is this right here. If I let u equal 2x plus 1, then du is just going to be 2 dx. So I'm going to get 1/2 du equals dx. So that's going to be able to take care of that underlined stuff. But what's missing is still this x in the numerator. So I'm going to come down here and I'm going to solve this equation for x. Also, these are x limits. So I have x equals 0, but then u would be 2x plus 1 would just be 1. And if x is 13, u would be 2x plus 1, which would be 2 times 13 plus 1, which would be 27. So what do we get here? Instead, that's probably a little too down too far. Instead of 0 to 13 for x, I have u going from 1 to 27. The top is x. That gets replaced with 1/2 u minus 1. The bottom is the cube root. 2x plus 1 is u. And then dx, oops, is 1/2 du. Okay, so now this 1/2 and this 1/2 can both be pulled out. So I get 1/4 integral 1 to 27. I just have u minus 1 over the cube root of u. So I rewrite the cube root of u as u to the 1/3. So this here, this u is u to the first, which would be u to the 3/3 power, right? So if I rewrite this, I split this into two fractions with a common denominator. U to the 3/3 over u to the 1/3 is u to the 2/3. 1 over u to the 1/3 is just u to the negative 1/3. Right? 1 over u to the 1/3. The 1/3 is in the bottom, so it would be a negative exponent. So I'm going to have to take 2/3 plus 1, so that would be 2/3 plus 3/3. And I'm going to have to take negative 1/3 plus 1, so that would be negative 1/3 plus 3/3. Oh, no more integral. I'm actually evaluating now. I'm taking the antiderivative. So it's going to go to u to the 5/3. But then I have to divide by the new exponent 5/3. U to the negative 1/3, when I add negative 1/3 plus 3/3, I get u to the 2/3. But then I'm going to have to divide by 2/3. And then this is being evaluated between 1 and 27. Dividing by 5/3 is the same thing as multiplying by 3/5. Dividing by 2/3 is the same thing as multiplying by 3/2. So I plug in 27. 3/5 times 27 to the 5/3 minus 3/2 times 27 to the 2/3 minus, I plug in 1, 3/5 times 1 to the 5/3 minus 3/2 times 1 to the 2/3. And all of this is affected by the 1/4. So don't forget that, right? That 1/4 has to be multiplied by everything we end up getting here. Also, we're having to remember the denominator is the root that we take. The numerator is the power that we take. So, (27) to the 5/3, we take the cube root of 27, which is 3, 3 to the 5th power. 3 times 3 times 3 times 3 times 3 is 243. 27 to the 3/2 power, 2/3 power. This 3 means I take the cube root of 27, which is 3. 3 squared is 9. This is easier. 1 to any power is 1. So 3 times 243, we get 729 over 5 minus 27 over 2. Let's see. Minus 3/5, and then minus a negative 3/2 becomes plus 3/2. Going to be running out of room here. So that's 1/4. 729 minus 3 becomes 726 over 5. Negative 27 plus 3 becomes negative 24 over 2. So I get 1/4. So I get 1/4. 726 over 5 minus 12. So that's 726 over 20 minus 3, which is 363 over 10 minus 3. 3 is 30 over 10, so we get 333 over 10. Barely fit there. So it's a little bit involved. Make sure you understand how the substitution is working for the limits of integration, and that's one of the more complicated of these u-substitution problems.